Hello, welcome to the course Transducers for Instrumentation. Last lecture we were discussing about the electrical and thermal networks, and we saw that the thermal networks can also be solved just like the electrical networks. For example, the resistances are replaced by the thermal resistance, the current flow is replaced by heat flow, the temperature difference is corresponding to the potential difference. So the similar kind of laws, just like the Ohm's law, they are applicable to the thermal network as well. So today we will discuss some thermal resistances and how we can connect them in series or parallel and how do we solve them. So we discuss thermal resistances in parallel. Thermal resistance which are in parallel. So for example, we have these two material are material A and material B with some thermal conductivity of Ka and Kb, and we want to investigate the thermal flow when these materials are connected in parallel. So for example, we have surface here which is surface of A and which is this is surface of B. So the first assumption we are making is across the surface of this material A, this surface, the temperature remains same. It means the temperature of the surface at this point is same across the surface. So this is the assumption, just like a point contact in electrical networks. So similarly, we have the same assumption in thermal networks. So this point has a temperature which is same across the surface. Similarly, for material B, this point has the same temperature across the surface. So this is the assumption we are making. Similarly, on the other surface, the far surface, we have this point where the temperature is same across the surface. And we assume that there is no thermal conduction between this surface. So there is no thermal power dissipation is not there across this. So given these assumptions, now we have a temperature difference which we apply across this assembly, and we want to investigate how the heat flows. So let's say we have a temperature which is T1 or TS1, whatever we call it. So this is the temperature we apply at the near end, at the far end. Let's say the temperature is TS2. Now we can write the resistance of each one of this material is, for example, that R conductive for a material A is equal to L upon Ka, which is the conductivity, multiplied by the area. So here the L is this and the area is cross section area of this material. So this is the R conduction for material A. Similarly, for R conduction B will be L upon Kb into A. the area of, for example, the area of material A is A subscript A, and the area of material B is A subscript B. So these are the thermal resistances of these material A and B, and because they are connected in parallel, we have the overall resistance, which is 1 upon R total equal to 1 upon R A plus 1 upon R B, or we can say this comes out 1 upon L upon Ka into AA plus 1 upon L upon Kb into AB. So this is the total resistance, which is our total of this whole assembly, and this is very similar to the parallel connection of electrical resistances. Now we can calculate the heat flow across this whole assembly when we apply this temperature difference, which is Ts1 on the near side and Ts2 is on the far side. So we can calculate the heat flow, which is equal to the temperature difference, which is Ts1 minus Ts2. This is the temperature difference, just like your potential difference, divided by the total resistance, which is R total. So this is the total heat flow, which is equal to the difference in the temperature divided by the total thermal resistance. This is very much equal to the electrical current which is flowing through the material, that is equal to the voltage difference divided by the resistance. So this is the parallel connection of these thermal resistances, though we can more generalize it by considering that one source will be supplying this heat energy to this assembly. So let's consider a little bit more generalized case. We have this material assembly. This is material A, this is material B, with thermal conductivity Ka and Kb respectively, and these are the points at the surface. Now we assume that there is a source of heat energy which is here at the temperature T1. This is supplying some heat which is going to both of the materials, one here from this point to this point and one from here, and this mode of heat transport is convection, because there is no direct contact between this point and this point. Similarly, on the far side we have a receiving end which is at temperature T2, and this heat is flowing from this point to the far end. This is also the convection mode. And inside the material, the mode of heat transport is conduction. Now we can write the resistance similarly to the previous slide, where we have 1 over R total equal to 1 upon RA plus 1 upon RB, the resistance of the path A and the resistance of path B. Now the path A has three subsections. One is this path where the heat is flowing from T1 to material A through the convection mode, and this is the second section where the mode of transport is conduction, and heat is flowing from this point to this point, and the third section is where the heat is again flowing through convection from the, the material A to the point T2. So we can write the overall resistance of the upper path like RA, the thermal resistance through path A is equal to 1 upon H1 into AA. Here the this H is the coefficient for convection. So 1 upon H1 into AA, which is the area of this surface AA, plus the second section, which is conduction, which we can write L upon Ka into AA, very similar to the last slide, and then again the third section, which is again convection, and we can write 1 upon H2 into AA. So this is the overall thermal resistance through the path A, and similarly we can write for the path B, which is again three section. This is first section, this is second section, and this is third section, and we can write for RB is equal to 1 upon H1 AB plus for the second section, which is conduction, that is L upon KB into area of B, plus the third section, which is again convection, 1 upon H2 into area of B. So these are the respective values of RA and RB, and we can calculate the total resistance. 1 upon R total is equal to 1 upon H1 AA plus L upon KA into AA plus 1 upon H2 to area of A plus 1 upon H1 into area of B plus L upon KB into area of B plus 1 upon H2 into area of B. So this is how we can write the total resistance of two materials when they are connected in parallel. And we can also write the equivalent model of this whole assembly, that we can write something like this. We have the first point, which is T1 here, similar to this. We have T1, and then we have the first resistance, which is in the form of convection, and the value of this is 1 upon H1 into AA. The second element in this is because of the conduction mode, and that is L upon Ka into area of A. And the third element, which is again because of the convection, to this temperature T2. The value of this is 1 upon H2 into area of A. So this is the model for the upper path. The lower path is also similar to this. The value of this we can write similarly, 1 upon H1 into area of B. This is L upon Kb into area of B, and this is 1 upon H2 into area of B. So this network is very similar to the electrical network, and we can apply any temperature difference T1 and T2 and calculate how much the heat will flow from the point T1 to the point T2. We can apply all kind of Ohm's law to calculate all this heat flow from T1 to T2. So we can write the heat flow for this assembly, which is again similar to the last slide, which is T1 minus T2 divided by R total. R total is the whole combination of this model. So this is the thermal resistance connection in parallel. Now we consider little complicated case where we have multiple materials joined together in terms of series and parallel, and see how we can calculate the heat flow in that whole assembly. So we calculate thermal resistance of series parallel network. So for example, we have assembly where we have different materials. This is material, for example, A, then we have material B, and we have material C, and another material is connected like this, which is material D. And correspondingly we have the thermal conductivity of these materials, which is Ka, Kb, Kc, and Kd. And the length of this material is, for example, La and Lb, Lb and is equal to Lc, and this is Ld. So this is the whole assembly of materials, and we want to calculate how much heat will be flowing through this assembly if we apply a certain temperature difference across this assembly. So let's say we apply a temperature difference which is T1 this side, and this side it is T2. Whole area of this is A. So now we need to make an assumption here. Similarly, in the first slide, we had assumption that at the point of contact, the temperature is same across the surface. So similar assumption we need to make here, that there is no temperature difference perpendicular to the x-axis. For example, the heat is flowing in the x-axis, in the x direction. The heat flow is this side, and there is no heat flow perpendicular to this. Means the surfaces which are normal to x direction, they are isothermal. The heat will not be flowing from material B to material C. The heat will be flowing only from material A to material B and material A to material C, and then back from material B to material D and material C to material D. So this is the assumption we need to make. This is the assumption that surfaces which are normal to x direction are isothermal. So they are at the same temperature of each other, and there is no heat flow in the perpendicular to x direction. Only the heat is flowing from T1 to T2 in x direction only. So now we can treat them like a four resistance, where we have this material A which has certain resistance, then we have two resistances corresponding to material B and material C, and then back to material D. And the value of these resistances we can calculate, just like for the conduction case, which is L upon LA upon Ka into area of A, and this is for material B, which is LB divided by Kb into area of B, which is actually half of the area of A, but we can write for generality area of B. This is material C, and we can write LC divided by Kc into area of C, and this is material D. We can write L of D divided by Kd into area of D, and the temperature applied is T1 this side and T2 this side. So we can solve for this series parallel connection, which is Ra plus Rb parallel Rc in series with Rd. That will be the total resistance, and the heat flow we can calculate T1 minus T2 divided by the total resistance. The heat flow for this network will be T1 minus T2 divided by the R total, and R total we can calculate of this thermal resistance. This is R total. So this is how we can solve a thermal network very similar to the electrical networks. We need to discuss one more point of the thermal resistance, which is equal to the contact resistance of electrical network. So similarly, in thermal networks we have thermal contact resistance, very similar to the electrical contact resistance. So this is the thermal contact resistance. So when we have two materials, let's say material A and we join this with material B, this is material A, this is material B, and there is a heat flow from the left to the right. Now when these two materials are joined together, they behave differently at the surfaces where they are having a contact with each other. That is called the contact resistance, which is different than internal their intrinsic resistances. So the reason for this is, for example, we have this surface which is in contact of the surface of material A is in contact with surface of material B. When we join them together, we assume that the whole surface is in contact with each other, but in practicality this is not the perfect contact. If we zoom in at this point, if we zoom at this point very closely and we see the surface is there is actually not in very much contact. If we assume that this should be the point of contact or the physical contact, actually the material A, let's take the material A with blue color, the material A surface is something like this. Because of the surface roughness, material A is like this, and the material B, the surface is like this. So we see that there is no proper contact between material A and material B because of the surface roughness. They are not very much in close contact. So now if the heat is flowing from material A to material B, that heat will have two paths. One is the path where they are in contact. Here material A is in contact with material B, so heat will have different resistance, which is, let's say, R1. This resistance will be different than this resistance where these materials are not in contact. This blue curve is very far away than the green curve, and we have the different resistance R2, and we can calculate whole of the resistances of this, which are different values because of the surface roughness, and this gives rise to the contact resistance or the thermal contact resistance. Thermal resistance arise due to surface roughness. And this is again just like a electrical contact resistance, this thermal contact resistance is also a problem in proper heat conduction, and that is why if we want to have a good heat conduction from material A to material B, generally we try to put some kind of epoxy on the surface of this so that the amount of surface which is in contact with each other, that increases and this contact resistance actually goes down. So we sometime put some epoxy or the thermal conductive epoxy to reduce this contact resistance. So this thermal contact resistance is very similar to the electrical contact resistance, where we apply some 4-point Kelvin probe method to get rid of the contact resistance. Similarly, we have thermal contact resistance in thermal networks. So next we discuss the thermal RC networks. We will consider some practical cases where we have multiple assemblies and we try to investigate how much the heat will be flowing from the source to the ambient temperature, and we will consider some real applications where we can apply these thermal networks and solve for the thermal power dissipation. So we consider the case of an IC package where we have a semiconductor IC, which is silicon based IC, and we have some epoxy connected to it and then some heat sink connected to it. The transistor on the silicon chip will be generating some heat, and how that heat will be transferred to the ambient temperature. So let's say we have a semiconductor which is silicon, and on this we have a P plus device made of P plus material, P plus doping on this silicon. Below this silicon we have some die attach, and below this we have some heat sink. So we have now 4 different materials here. The first material is the P plus or P plus well. We can assume it's like a resistance which is generating heat when we apply a voltage across it, and this P well has certain thermal resistance which is RTH, let's say this is 1, and certain capacitance, the thermal capacitance, let's say CTH1. Similarly, we have another material which is silicon, and the RTH2 is the thermal resistance of silicon, and CTH2 is the thermal capacitance of silicon. The third material here is this die attach, and thermal resistance is, let's say, RTH3, and CTH3 is the thermal capacitance. And after this we have the lid frame, or after that we will have heat sink. So now we have this whole assembly which is practical assembly in any electronic circuit. Now we need to make a model of this whole assembly so that we can solve it for power dissipation. So we can make a model similar to this. This is the delta T, which is the temperature difference being generated by this P plus. This is T junction. Then we have a thermal capacitance connected to it, which is CTH1 and RTH1. Then this is connected to silicon, which is CTH2, and RTH2. Then again the die attach is connected to it, which is CTH3 and RTH3. So this is the whole assembly till this die attach, and further a heat sink is connected to this. Let's take the different color. Here this heat sink is connected, which is dissipating this heat to outside environment, which can be modeled just like a thermal capacitor, and a thermal resistance which is in low in magnitude. So this is heat sink. Now when the junction or the device inside this chip, they are generating heat, that heat need to be flowed outside to the environment, because the junction temperature has its limits. The junction temperature should not exceed a certain value so that the device can perform its operation satisfactorily. So we need to have this whole network efficient enough so that the heat generated inside, or this delta T, the heat can be transferred from this junction to the outside environment. Now typically in data sheets a value of RTH is given. For DC case, the value of CTH, the thermal capacitance, is not given generally, because we assume that in steady state condition, or where the heat is flowing in steady state condition, there is no transient there, this capacitance can be omitted. So this thermal capacitance is exactly like our electrical capacitance, where in the case of DC currents the capacitance can be removed. Similarly, for the steady state condition of heat flow, these thermal capacitances can also be omitted, and we can easily calculate how much current will be flowing just based on the thermal resistance, which is here in series, RTH1 plus RTH2 plus RTH3. So in data sheets typically CTH value is not included, because in case of steady state these can be omitted. CTH can be removed from this model. So the steady state condition for thermal RC network is very easy to solve. We just need to remove all the thermal capacitances and just the thermal resistances will be added in series or parallel, whatever is the case, and we can calculate how much heat will be flowing. Based on that, we can calculate how much junction temperature will rise, and this rise need to be within the limits of semiconductor devices uh, specified by the data sheet. So next, so this is the thermal RC network for DC conditions or steady state conditions. Let's calculate one example. A switch has its resistance, which is RDS on, equal to 24 milliohm. This is the electrical resistance, and the current flowing through this switch is 5 amp. I is 5 amp. So this is the electrical switch. Of 24 milliohm, and the current is 5 amp. The maximum thermal resistance RTH, is equal to 55 degree centigrade per watt. Ambient temperature, which is T ambient or TA, is 85 degree centigrade. We need to find the junction temperature. So now first we can see this. We have an electrical resistance which is dissipating some power. Then we need to calculate how much power it is burning. That power will be in terms of heat, and that heat will be flowing from this resistor to the ambient temperature, to the ambient, and the thermal resistance of this resistance is 55 degree centigrade per watt, and ambient temperature is given to 85. How much junction will temperature will rise? So first we calculate how much power is being generated. So the power dissipation is equal to I square R, 5 square multiplied by 24 milliohm. This comes out to be 0.6 watt. So this 0.6 watt of power is being generated by this electrical resistance, and this power, because this is burned inside this resistance, this is in terms of heat. This heat is going to flow outside depending upon the junction temperature difference and the ambient temperature difference. So the thermal resistance is given is as 55 degree centigrade per watt, means for a heat flow of 1 watt, junction temperature will rise 55 degree centigrade. So the total junction temperature will be equal to the ambient temperature plus the temperature rise because of the heat flow. So we can write TA, which is the ambient temperature, plus the thermal resistance, which is 55 degrees centigrade per watt, into the power dissipated, which is 0.6 watt. So this temperature is 85 plus 33, it comes out to be 118 degrees centigrade. So this is the junction. It means the junction temperature will rise to a steady state value of 118 degrees centigrade when the ambient temperature is 85 degree. Based on, and this temperature rise is due to the electrical power dissipation which is being happening inside the resistance. So this is the simple case of DC condition where we are assuming that there is no transient response and the heat is flowing continuously from the resistance to the ambient temperature. Next, we consider a more generalized case of transient response where the heat is actually being generated through pulses. It's not a steady state condition where the source is at a particular temperature and the heat is flowing steady state. Now the source, which is an electrical device, that is being turned on and off, and that will generate some transient response in the heat flow. So that we consider in transient response. So if we try to solve the same model which we just saw here, this is the model of this thermal network, which is very similar to electrical network, and we try to solve with this series and parallel connection of resistance and capacitance. We will get expression very similar to what we have in electrical networks, and the total impedance, now we call it Z in terms of omega, which is the angular frequency. So the model will look something like this, which is 1 upon 1 upon j omega C Thevenin plus 1 upon R thermal 1 plus 1 upon j omega C thermal 2, this C thermal 1 plus 1 upon R thermal 2, and plus this will continue till the last element. It depends on how many number of elements we have. We will get this kind of expression. Now looking at this expression, we can say that this model is fairly complex, and this is difficult to solve. We have, in practical cases, we have multiple thermal resistances and thermal capacitances. So the number of terms in this expression will be very high. So we do not want to solve this kind of model for our practical network. So what we have in real practice is a thermal graph, and this thermal graph is generated by industries based on that, they do extensive characterization of their assemblies and they come up with this thermal graph. Using this thermal graph, we can apply a pulse and calculate how much the thermal resistance will be there for that particular assembly. And this thermal resistance is particular to that thermal assembly. It's not usable by any other assembly. So this thermal graph looks something like this. So this is a thermal graph which is generated by the industries by extensive characterization. So what this thermal graph says, on the y-axis we have this junction thermal resistance, and on the x-axis we have the T pulse, which is the time period of the pulse. Now in the case of periodic event, when we have pulse applied to the network, let's say this pulse rises at this point and fall at this point. So this time between rising and falling, this is the time which is T pulse compared to the total time period, which is T, and the duty cycle of this pulse is given by D, which is equal to T pulse upon T. So in this particular case, we have duty cycle of 50% because half of the time the pulse is on and half of the time the pulse is off. So this thermal graph has multiple tracks on this. For example, this is the case for single pulse, where we just apply one pulse, it turns on and turns off and it remains there. There's no extra pulses. So in the case of single pulse, we take this graph. If the duty cycle of our pulse which is applied here is 1%, then we take this graph 1%. If we have 10%, we take this graph, and if the duty cycle is 50%, we take this graph. So this is how we take this thermal graph and we calculate how much the thermal resistance of our assembly will be. So using this graph, we can calculate our thermal resistance instead of solving this complex model. So instead of this complex model, we go for thermal graph. Let's take one example of transient temperature. In this example, we have a certain assembly and we apply a single pulse of 400 watt to this semiconductor package for 200 microseconds. So let me draw this pulse. So we have a pulse which is this pulse is 400 watt in magnitude, and the T pulse is 200 microsecond. This is time, this is 200 microsecond, and this is power. So this is the pulse which we apply to a certain assembly, for which we are given the thermal graph, and we need to calculate how much junction temperature will rise for that particular assembly. And the ambient temperature, generally it is 25 degrees centigrade, or the T ambient is 25 degrees centigrade. Now we need to calculate the junction temperature. So how to solve this? We are given that the power dissipation is 400 watt, because the power of this pulse is 400 watt. The thermal resistance, now we need to calculate that for this assembly how much will be the thermal resistance. Remember, if we actually solve the package for this thermal resistance, we may have multiple thermal resistances. For example, the silicon will have its own thermal resistance, ceramic package, dyes, bonds, every element will have its own thermal resistance. So instead of using that, we go for a thermal graph, and in thermal graph we need to know what is the duty cycle. So here it is a single pulse, it's a single pulse. We need to calculate the thermal resistance of this for 200 microsecond. So let's go to the thermal. This is the thermal graph, and for single pulse we need to take this graph, which is for this single case, and we can see for 200 microsecond, here it is around 200 microsecond, the value will be around 0.083 degree centigrade per watt. So this we can calculate 0.083 through this thermal graph, and we take this back to our calculation. The thermal resistance is equal to 0.083 degree centigrade per watt. Now the total junction temperature will be equal to T ambient plus the temperature rise, which is the power dissipated, into the thermal resistance, which is equal to 25 degree plus 400 into 0.083. This comes out to be 58 degrees centigrade. So the junction temperature Tj will be 85 degrees centigrade, and if we plot this rise in the temperature, it will look something like this. We have this time axis, and this is the junction temperature, which will rise when there is a power dissipated. This will be originally at 25 degrees centigrade. This is 25, and this will rise to its peak value and then again fell down, and this peak value will be at 58 degrees centigrade. So this is how we can calculate the junction temperature of the whole assembly. So this example is in case of single pulse where we have applied just only one rising and one falling edge. Let's take one more example where instead of one single pulse we apply the train of pulses to this assembly and calculate how much the temperature will rise. For comparison, we will take the time period as same as 200 microsecond, but now we will take the power which is very less compared to the last slide. Now we take 1.44 watt only as the peak power. So this is the PD, this is time, and we apply these pulses which is in 1.44 watt of magnitude, and the time is T pulse is 200 microsecond, and duty cycle is 50%. The ambient temperature is same as 25 degrees centigrade. Now we want to calculate how much junction temperature will rise if we apply this train of pulses. So the power dissipation is same as given to us. The power dissipation is given to us as 1.44 watt. We need to calculate the thermal resistance. So this thermal resistance we need to calculate through the thermal graph. Our duty cycle is 50% and the time T pulse is still same as 200 microsecond. So we go back to that thermal graph. Here for the duty cycle of 50% we need to take this graph which is shown here. This is for 50% duty cycle, and for the same 200 microsecond, this is approximately 200 microsecond. The junction temperature, the thermal resistance ZTH comes out to be 23 degrees centigrade per watt. This is approximately 23. So this reading we can take from thermal graph and put it back here, which is 23. Now we can calculate the junction temperature. Is equal to ambient temperature plus the temperature rise, which is PD into ZTH, the thermal resistance. This is 25 degree plus 1.44 watt into 23 degrees centigrade per watt. This comes out to be 58 degrees centigrade. This is the junction temperature. So this is the case in terms of periodic pulses, where we have this periodic pulse applied to the assembly, and this is the temperature rise. If we plot this junction temperature with respect to time, the graph will look something like this. We have initial temperature which is 25 degree, and the temperature will rise when the pulse is applied. Then it will go back, then again it will rise, then it will go back, then it will go rise, then it will go back. So it will achieve a peak temperature which is given by 58 degrees centigrade. So in steady state condition, when we keep on applying these pulses, the temperature will rise to 58 degrees centigrade. One thing to note here is, in the last slide we applied 400 watt of power, but the pulse was a single pulse, so the temperature rise was also 58 degree. But if we apply a train of pulses, even if the magnitude is very less, which is 1.44 watt compared to the 400 watt earlier, the temperature rise is still same, because these periodic pulses will keep on raising the temperature of the assembly and causes a more rise in the temperature, which is not beneficial for semiconductor devices. So this is how we solve all these thermal networks. It's very similar to the electrical networks. So this is all for today. Thank you.